Okay, let's try that. And hopefully, oh, come on, man. You were not doing this earlier. Well, I guess it won't matter. Huh. Oh. Oh well. Okay, so it's this lab we're going to be working on today. Lab. It's a worksheet. You know, it's a set of problems that we're going to deal with. And basically what we're doing is we're going to take the KC from chapter 5, the equilibrium, the law of mass action equation thing, and apply it to weak acids and weak bases that set up an equilibrium reaction. And so what you'll turn in next Thursday, the first page doesn't matter. The first page is actually a worked out exercise that I'll sort of go over briefly in a minute or two. But what you'll turn in, well, I'll just put a little check mark. You'll turn in the second page. We'll go ahead and turn in the third page, even though there's issues there. We'll talk about it a little bit. You're going to turn in the fourth page and the fifth page. That's it. This last part we're going to skip for now. This last part, I'll talk about material related to that last part, but that last question we're not going to do. So really, it's just 3 problems. I'm not going to lecture the full 2 hour, 40 minutes, whatever this class period is now. If you want to, you can stick around and answer them. There'll be enough time for that, I think. And ask me questions, blah, blah, blah. Anyway, let's talk about these questions here. Now, these are, okay, so the table that you see there, it's an ICE table. Okay, so something we did from chapter 15. And the form of that table, right, it's the same form every single time. Okay, and what's different is that you're given a different acid or base depending on the, so I'm looking at this is page 58 in the lab manual.
I think it's 56.
Is it 56? Okay, so 56 is that guy.
No, excuse me, I'm sorry, second table. Our first table will fill in.
Okay, thank you.
My apologies.
Nope, no problem, thank you. So 56, so minus 2, 57. Okay. So let's look at this one that is already filled out, okay? So you got to go through, quite a bit of hoops to actually do the calculation. But really, the main thing here, the main point, is to calculate the pH of a given solution. That's what we're after. And so it's like this answer is, like when I grade this, the first box I'll look at is that pH. And if that pH is correct, I sort of relax and sort of, does the work look okay? If that pH is wrong, based on my key, then I'm like, okay, I'm paying a little bit more closer attention. So it's really that pH value that you're shooting for. And you basically have to, fill out this ICE table to get to that point. And let me point out, notice down here. So again, this first page is a worked out exercise for one of these ICE tables. So that pH calculation, that last line there, is what you're ultimately calculating the pH. And I'll go through a problem showing you how this all breaks down, okay? But I just want to give you a little bit of perspective about what pieces go where in a problem like this. And then the other little tidbit that you see here is this side of the table. It's not, you don't have to draw this for an ICE table for the test or anything like that, okay? It's just an extra table I put in there because there's a whole set of calculations associated with the equilibrium constants that are associated with weak acids and weak bases. And I'll go over that today as well, all right? Now, in this particular problem, what happened was I gave you that answer, or that information, I should say, the Ka for the acid, which this is acetic acid, okay? So common acid, 5% is vinegar. You use that in the calculation, obviously. And then these other little tidbits here, you got to calculate those. And I'll show you how to do that today, okay? And the same thing goes for the rest of this. So let's just, look at one of these. Look at what you got. Instead of the Ka, not that. Instead of the Ka, I give you something called the pKa. Again, I will talk about that in a minute. And then, all right, ultimately, calculation is how you calculate the pH for this particular compound. Now, notice the salt formula that we're looking at there. Ammonium nitrate. Right, we need to be able to recognize that it's the ammonium ion there that's going to be acidic. The nitrate, the nitrate is a conjugate base of a strong acid. Therefore, it does not affect the pH. It's almost like a little mantra for chapter 16. So that nitrate does not affect the pH. So when you're talking about hydrolysis reaction, it's this. And then you're set to then fill out the ICE table. Oop, there's a charge there. You can put the AQ tag and L tag for water if you want to. At this point, I don't care. Okay, so again, just trying to set the stage just a little bit. And maybe I should comment one little other thing. So since what's called the pKa is given on that table on the left-hand side, you use that information to then calculate all the other bits of data questions there. Okay, and I will go through that with you. Bless you. Repeat, 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 repeat. There's 6 of these that you'll need to do. Okay? Okay, let's go to a question from the lecture slides. So this is on page 9 of the lecture slide. It's dealing with weak acids there. Okay. And the problem I'm actually going to work is, and I'm sort of setting the stage here with niacin. It's actually going to be, notice down here at the bottom. I went ahead and sort of remind myself what I'm going to go through. So it's practice exercise 10 is what I want to do. And notice what's setting up here. The Ka for, it's a monoprotic acid. It's a monoprotic weak acid, and I'll talk about that in a minute. Niacin. That Ka is given. The pH is the question mark, and then a particular concentration is given. That's the same structure that we saw. I'll come back to this in just a second. It's the same structure that we saw here. There's a concentration, there's a Ka that's given, and then you go through this ICE table to do the pH calculation. Okay? So basically, the example that I'm going to do in the notes here is analogous to what you have to do for the lab. Let's talk about niacin and the equilibrium constant just for a second here. Okay, so I've rewritten niacin structure is right there. And notice it has that, oops, sorry, I should move that up. Notice it has that COOH pattern to it. So it is a weak acid, right? It's that proton there that can be kicked off in solution. Do you see something else about this molecule based on what we talked about yesterday? Yeah. So in other cases, that nitrogen, I'm going to erase this because it's not relevant to the problem, but that nitrogen in there could act as a base in other examples. Right? That's not what we're out about, but I'm just curious if anyone noticed that. Now, I think when you put niacin in an aqueous solution and you test the pH is going to be acidic because that proton is a stronger acid than that nitrogen is a base. Now, for our purposes here, we're just going to treat it as a monoprotic acid. We got that hydrogen is that hydrogen. I just rewrote the molecular formula here. Okay. For what it's worth, okay, that ring structure you see there are carbon atoms at each of those points there. This is not relevant, but it does help explain a little bit about what's going on. In organic chemistry, there's a couple different shorthands that we use to draw structures, and this is one of them. You do not need to know how to draw the structure. You just need to know. You need to recognize it's a monoprotic acid, and that what I'm about to show now in terms of like IC table, blah, blah, blah. All right. Now, one other little thing I'm going to do here is I'm going to change the notation, and I'm just going to put HNic. So instead of rewriting that molecular formula over and over again, I'm just going to put Nic for niacin. All right. I could have used HA. I could use H anything, because really the only thing I care about is the monoprotic acid, and it has a particular Ka value. So let's set up the structure of this reaction here. And well, first step, let's just do this. Step one, and we'll talk about that later in just a second or two. Right, hydrolysis reaction. That's what we do all the time. We take our niacin, our monoprotic acid, we react it with water. You know, it is a weak acid because it's not one of the 7 strong acids. That's true always for us. Proton gets donated over. We have an anion now. And we have hydronium. And again, if you want to, you can put in the AQ and L tags, but I'm not going to worry about it at this point. All right, so like this guy here, that would be its conjugate base. Just to sort of tag with something we talked about in class. You know what? Actually, I am going to add the phases here because they're actually relevant. Just hit me. This has been a while since I've lectured on this material. In chapter 15, we would have called that a heterogeneous equilibrium, meaning we have aqueous and liquid phases together. In chapter 15, we learned that pure liquids and pure solids are omitted from the law of mass action equation. Law of mass action equation is this little beast, and I'm going to start out talking about, right, it's AQ, it's molarity. For these examples, we would have Kc in chapter 15. Well, to be a little bit more specific, instead of Kc, it's Ka for acid. So if you see a capital K pretty much anywhere in the book, That is in reference to some kind of equilibrium constant. The subscript is just associated with that type of reaction or that type of reactant. Ka for acids, Kb for bases, KSP, actually we'll learn that for insoluble salts, Kf for metal ligand complexes like we saw last week. So there's a bunch of these different ones, but they're all done the same way. Products over reactants. Just like in chapter 15. The products here, it's the conjugate base, concentration of it, concentration of hydronium divided by the concentration of our original acid. Nic, H-Nic. And then that Ka value is given in this problem. All right. Since that exponent is small, that is how we know. This is another way we know it's a weak acid, by the way. We'll come back to that in just a second. First, let's just look at some of these other examples over here. This is just a table from the textbook. It's just a bunch of miscellaneous weak acids. You don't need to memorize these numbers. Kas and Kbs and pKas and pKbs will be given to you on the test. Or you would have enough information in the problem to calculate the Ka or the et cetera, et cetera. And the way they've laid this out, notice what's happening over here. All right, we're going from large number to small number. Or maybe I should say small number up here to smaller number down there. It doesn't really matter. I mean, 10 to the minus 2 for chlorous acid, and then phenol is 10 to the minus 10. Like chlorous acid, I'm not going to write it down because it's a strange wording. Chlorous acid is like a strong weak acid, if you will. You know, it doesn't disassociate very much, but in the grand scheme of things, as a weak acid, it's pretty strong. Okay, because it has that 10 to the minus 2. And so you can actually, you know, and they have arranged this in what descending acid strength. So the smaller the Ka, the weaker the acid. Weakest acid. Oops. I keep forgetting to move it up for y'all. Now, let's just take a moment. Let's just compare that with like a real strong acid, like HCl. And let me just quickly write out the hydrolysis reaction. Fine. That's a bona fide strong acid. There's basically, we're talking about, 100% dissociation. We don't talk about Ka values for such things just because, there's so much chloride and hydronium in the solution that we can pretty much ignore everything else there. But I've seen values, sort of the approximate Ka value of something like 10 to the 7, I believe. It's a positive exponent. Strong acids have positive exponents, and these weak acids have negative exponents. That's sort of a, casual division. Yeah. Yep. Good. Yep. Now again, Right. That's basically a true statement. And I may be a little bit off, okay, in terms of 10 to the minus 4, 10 to the minus 6. It really doesn't matter because they all disassociate. Okay. So great. We have this, and we'll go to exercise 10 in just a second. I just want to make some additional comments here. Okay, so we have this Ka value in front of us. And remember, the problem is actually wanting to know what the pH of this solution is. We have not talked about pH yet. We'll talk about that in class tomorrow. I'm hoping I can just get away with this equation with us today. And then talk a little bit about it conceptually. Okay? So pH, it's a mathematical formula. It's the negative log of the hydronium ion concentration. And if you look at your equation, you do have that. You know, it's sitting right there. So basically, what we're going to wind up doing is like taking like this chunk of the problem, solving for hydronium, and we'll get a number out of that, and then we'll be able to and then plug it into our equation here to get the pH of the solution.
Is pH in general like the negative log of hydronium, or is it of the like conjugate base or acid?
It's specifically of hydronium.
Okay.
Yeah, so yeah, like it doesn't matter what weak acid, weak base, strong acid, strong base we're talking about. When you measure pH, it's always in reference to hydronium that's in solution. Okay. So hydronium, right? That was that characteristic molecule associated with an acid. Well, as it turns out, there is another equation that can be useful here, and that is for hydroxide. Same kind of setup. Right? Hydroxide ions are characteristic of bases, and so what we say is the POH is equal to the negative log of the hydronium concentration. Kind of the pattern that we see here is if you see a P in front of some expression, what you just did was take the negative log of something that's related to that expression. In this case, hydronium concentration and hydroxide concentration.
Do those two things have a necessary relationship with one another?
They do. Yeah.
You could just use one and theoretically get to the other.
Yeah, and we'll see those equations in just a minute. It, actually, pH plus POH equals 14.
Hence 14.
Who knew, right? We'll see. You'll see why that's 14 in a minute or two. Again, I won't do the full spiel today, but at least maybe just a little nugget. While I'm talking about it, I've mentioned pKa up to this point. Well, if you see the P, and I say you'll just take the negative log of something, what am I taking the negative log of? Good, the Ka. The Ka value. And I can't do that in my head. I don't think I have. Do I have it in front of me? No, I don't. Anyway. It's 4 something. I know it's 4 something. And I don't have a calculator that can do it either. If you say pKb, it's negative log of something called the, and I shouldn't put brackets there. I don't need brackets, do I? So pKb would be the negative log of the Kb. And, oh hell, I'll just write it out. I've been saying it. pH plus POH equals 14. As it turns out, pKa plus pKb equals 14. So that number 14 isn't like numerology or anything. It does pop out of an equation that we'll visit. It's not magic. But those equations are really helpful because they're simple. I I can almost do that without a calculator. If I had the pKa, I could almost calculate pKb without a calculator. Actually, I could do that, I think. The other way to do this, no, you need a calculator. Probably. You know what? Let's just jump into the problem. Let's not yammer on about pKa's and all that. Let's revisit number 10 here and actually do this calculation for real. We have enough information. Let me, let's see. I'll need an ICE table. Great. Let me set that up. I'm going to rewrite the equation we saw just a second ago. Nope. Hydronium. Oh, I might as well. Let me add the AQ and L since we're heterogeneous equilibrium. I'm going to go ahead and just set it up here. We need an ICE table. I think we've only done that once, but maybe twice. Now it's second or third time. If I look at the data that's given to me, there's not much data there. Excuse me, that's okay. It says that we have a solution of niacin at 0.01 molar. Now that's the original concentration of niacin that we place into the water. That would be its initial concentration.
If they give you a volume, would you then have to take the step of calculating the moles?
You could still use molarity.
Okay.
Yeah, for the ICE table, moles or molarity will work. Yeah. Actually, just a little, let's make a little note. So moles, molarity, or actually atmosphere, partial pressure if it's a gas phase. So grams don't work. Liters, ooh, don't use liters. Let's not do that. If it's a gas phase, yeah. Those are the three that we'll use. So that initial concentration there, that value that would like be written on the bottle, that 0.010 molar, that is the amount of niacin that you add to the water. And if you think for a minute, as soon as it hits the water, let's imagine it's not ionized. That's the initial state. Nothing has ionized. Well, what that means is that the conjugate base and the hydronium initially is 0. Initially literally means initially. Nothing's happened yet. Okay? That is useful in a minute or two. What about water? Well, water wasn't in our Ka expression, which I'll rewrite in just a second. And so pure liquids, pure solids are omitted. You don't have to worry about it in the ICE table. Let me go ahead and rewrite the Ka expression that I wrote up a minute ago. Why did it change? I don't know. Doesn't matter. Oop. Let me move that up. And hydronium and H Nick down here. And it has a K value. I'm not going to rewrite it right now because I've got to work with that formula in just a second. Now, something I mentioned last week when working with an ICE table, right? There's two things you got to do. You got to there's a plus and minus side. One side's going to add stuff, the other side's going to lose stuff, and then I think the other one to factor in molar coefficients. Now in this case, unfortunately, most of the actually maybe all the examples, it's just a 1 to 1 to 1. even for like a di or triprotic acid, we still do one step at a time. Okay, so that it does simplify our life quite a bit. And then I guess, right, we use this idea of X as the amount of change, if you will. Right, we don't know what the change is. X is an unknown. So if I start with 0, I'm starting with 0 niacin, 0 hydronium, well, the equilibrium reaction will take place. Not much will form, but some will form. Right? Some positive value X, our unknown. We don't know how much it's going to form yet. So if the product side is positive, then the reactant side is negative by the same amount. Again, because you have that 1 to 1 to 1. You don't have to worry about. I think the example from last week, there was a 2 showing up. Yeah. So in a lot of ways, the chapter 16 examples are a little bit cleaner. You don't have to worry about molar coefficients all that much. And now if I kind of read this expression, what's happening at equilibrium? Well, it starts to take on the form of a mathematical expression. Actually, let me, instead of one big X there, let me get rid of that one big X. So I just have the X of interest. I'm basically adding up E and C, the initial and the change. All right, I started with that concentration and I lost a certain amount. And when that happens, then I'll have some equilibrium value that's represented by that 0.010 minus X.
So you knew what was being added or subtracted because of, like, you started with zeros on the product side. But if that wasn't the case, like, would you have to look at, like, the Ka value? Or?
Yeah, so the examples you're going to see, there'll be 0 somewhere.
Okay.
Yeah. So go toward the 0. Yeah. Nature is going to feel. Nature abhors a vacuum. Who is that? Descartes or something? Anyone? Anyone? Yeah. That's my UNCA training in the humanities. But yeah, that's true. I mean, nature always goes towards something that is 0. That's why vacuums are a bit challenging. I mean, you can pull a vacuum, but if you really want to pull a serious vacuum, I mean, that's a lot of work. Just because every single air particle is trying to get into that space because there's nothing there. So there'll be a 0 that you'll shoot for. And then that would establish the positive side. So I'm a little closer, right? Let's just keep our eye on the ball here. Right? Ultimately, I want to calculate the pH. Oops, sorry. And right, the pH is this expression. Now I know that the hydronium concentration value is X because of that. So I need to, now I'm going to set up an algebraic expression. I'm going to solve for X. I'm going to, once I have X, then I just plug it into the pH value to then, or the pH formula to get the pH of that solution, okay? Based on the Ka. Let's do that. And what this looks like is something like this. Right? These concentrations in the Ka expression, that is dealing with the equilibrium line. Right? Ka is always about equilibrium state. So I know the concentration of that conjugate base, it's X. I know the concentration of hydronium, it's X. Well, I don't know, but I have an expression that I can stand in for that. And then I have this thing for the niacin that I start with, right? Reactants over products.
So you have to use the equilibrium concept.
Yes. Yeah. So, yep. I'll tell you a story. I'm always saying, oh, uh-oh, like that. My dog, whenever she hears that, she just goes crazy because she knows something's wrong. And I'll accidentally say, uh-oh, and here she comes barking. Cue to the button. Okay. Yeah, so this equilibrium expression is what's going in there. Now, how do I say this? How do I approach this? If we, here we go. Let me do this. Now, at this point, where's the knot? There's the Ka. This produces, this expression can be solved as is. You can solve for x, blah, blah, blah. To do that, like old school, you got to go through the quadratic formula. We don't want to do that, okay? We don't. We really do not want to do that. On some examples, not for the next test. The next test will not involve quadratic formulas, okay, just to be clear. But in some examples, you do have to worry about quadratic formula if you do it old school way. The other way to do it is actually you can plot these two sides onto a graphing calculator where the two lines intersect. That's the value for x. You can do that as well. And one of my students, actually many of my students, they've pre-programmed that formula in. Because the only thing that's changing, the two things that are changing is that concentration changes from one problem to x, and then the Ka value changes from one problem to x. And that's it. And so, I mean, if you set that up properly, you don't have to think in a way. You just plug in those two values, and then x is calculated for you. Right? So you can take advantage of your calculators if you want to do that for the test. Now, fortunately, there is an approximation that we can use. So let's look at that approximation. And I'm just going to go ahead and write it out in its correct form. This you can solve without the quadratic formula. And it will give you a value that's essentially the same as the x above. So the only thing I'm getting rid of here is that minus x. Right? That's missing from that expression. You know what? Let me not go through a full song and dance right now. I'll do it in a minute. Let's just answer this. Let's just get this off our plate. There's the number. So let me just take a couple of steps here. And I'm going to keep that in blue. So if I start solving this, so xx is x squared. If I multiply both sides by the 0.01 to get rid of it from beneath the expression on the left, I get 10 to the minus 7. And then I got to take the square root of both sides to get rid of the square. And that gives me a number, 4.0 times 10 to the minus 4. And I'm going to go ahead and insert molarity because that is what we're talking about. So you got to work through a little bit of algebra there to solve for x. I'll be happy to talk about that outside of class, okay? Once you have this value, all right, how many colors can I possibly make? And I did it again. Ooh, plenty of colors. Right, I'm just going to insert it into that value right there, that formula right there. and I'm ready. I'm done. So now the pH is equal to the negative log of 4.0 times 10 to the minus 4, and that is equal to 3.40. So it's a reasonably low pH for niacin at this concentration. Just remember the sig figs. Why am I thinking we did this before back in chapter 4? Did we talk about sig figs for logs? We did not. We did not. Let's talk about that. So the sig fig for logs, what you see here is, oh, I don't have, oh shoot. Well, however many numbers you have here in the expression, that equates to the number of decimal places in the final answer here for logs. So it's just another log rule, sig fig rule for logs. Just like he's had, if you go back to chapter 2 in the textbook, there's a rule for addition and subtraction. There's a separate rule for multiplication and division. There's another rule for logs and natural logs, and that's it. So again, the number of digits here in our scientific notation expression, or another way to say it, is the number of significant figures in our concentration, because that's essentially what we have. Now, our hydronium concentration or hydroxide concentration or whatever we insert into our log is going to be in the scientific notation form. So all the digits up front, that represents all the sig figs in that value. Number of sig figs there dictate how many decimals that you're going to have there. And that's it. So pH about 3.40 or so for this solution. And that's with that approximation. If you use the quadratic formula and went through blah, 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 all this, the answer would probably be, and I'm just guessing, 3.42. Thank you. Yeah. So it's a difference of 0.02. And that doesn't matter, honestly.
If this were a multiple choice question, would it have the answers as the approximation or as the
If it is a multiple choice question that would require the use of quadratic formula, then the approximation would not be used. Okay? So we'll talk about when an approximation is valid or not later. Because for us, for like the test coming up next week, you don't have to worry about it. You can use the approximation for all of them. Okay. Or like if you set up your calculator to, there's actually another way you can do it. You can even, let's not even talk about it because it's not going to be on the test. Pooey, let's go on. Let's talk about the approximation here. What am I doing?
What is the limit where you can just drop that X?
The ionization, if it's over 5%. And that's something I'm not going to worry about today since we're not worried about quadratic formula. The ionization here is pretty low. And so as long as the ionization is low, you can think of the percent ionization, I, is how far it goes onto the product side. 2%, 3%. This one's probably, this one, I don't know, do I have it? It's 4%. The ionization here is about 4%. We'll do that later, like in class later. If the ionization is too high, above 5%, then this approximation that I'm about to talk about doesn't work. So the key point here, and I'll just write it out. If percent ionization is low, then X is very small. So small, in fact, and you could do this math actually, but we won't. I mean, if you plug in 0.01 minus X, with X being that 10 to the minus 4, I mean, it's going to be like 0.009999 or something like that. You know, it's a really small number. It's a really small change. So whether we carry the X here or not, it really doesn't matter. That initial concentration of niacin doesn't change that much since the ionization is so low. And so we can get away with just using that raw number that we started with. If that ionization is too high, then it shifts that number so low at equilibrium that you have to factor in the X, and that's when you have to use the quadratic formula. And that's for after test 2. Right? Okay. We're going to do another ICE table in just a second. But before I do that, let's just look at the pH scale. I really don't want to talk about it because I want to talk about it tomorrow. But there's the pH scale. I sort of probably familiar with a lot of this. There's that pH value sitting there. Notice there's the pOH that I mentioned a few minutes ago. And, right, this statement is still true. pH plus pOH equals 14. You could do that all the way down the list and you would find that. So basically what the pH and the pOH is telling you is a concentration of their respective ions. So when something is really acidic, then you're talking about, it's still a low concentration of hydronium or H+, the notation doesn't really matter. It's representing the same molecule. You know, it's still kind of small, but on a pH scale, it's the biggest thing you got. 10 to the minus 1, 10 to the minus 2. pH is 7, right? That's neutral. That's the only place where hydronium and hydroxide are equal to each other. You can see it 10 to the minus 7, 10 to the minus 7. We'll talk about where that comes from later. And then as you start going to a lower and lower concentration of hydronium, which is ultimately what we measure pH by, then that value bumps up to a larger number. Notice that in the log, when you play the log game, notice how it corresponds to, the exponent corresponds closely to the value. If it's 1, it's exact. Most examples are not 1, and it's close to that number. That's when, I don't know if, I think I said it out loud. But like once I got to this point and I saw the exponent as 0.4, I knew that the pH value was close to that. I knew it was a little bit under 4 because, you know, as that increases, it starts shifting it lower than what the exponent actually is. But it's just a little mathematical pattern that you see in nature, these examples. That's enough for right now. I don't want to get bogged down. I really want to. I want to get bogged down in something else. Where is he? There he is. Yikes. No, it's not that bad. So this is page 16 on the slides. And I definitely need my notes for this. There they are. There's a bunch of equations over here. Let's not, actually, there. Let's not even be tempted by that. Let's just look at this chart for a second. Okay. So one thing to note is, so we have a representative strong acid, nitric acid, and we can say something about its base. Its base, or I should say, we can say something about its conjugate base. Its conjugate base is not basic. right? If you add just nitrate into a solution, the pH is still going to be 7, right? Nitrate does not affect the base of the solution. But any other acid, any weak acid, well, these are weak acids. When they dissociate in solution, they are going to form conjugate bases that are now weak bases. We saw the example that niacin had a particular Ka. All weak acids have a Ka value. Right, and you can look at this and say, okay, -4 down to -11. This is less acidic as I move down that value. And so hydrofluoric acid is the strongest weak acid on our list. In some ways, I almost want to just. He's really not in the conversation here. Okay, we can talk about these other ones. And we have a KB, which tells us, right, how basic the conjugate bases are there. Now, I'm going to focus on not Ka and Kb, but I'm going to focus on pKa. And actually, let's just, I want a different color here because I know I want some contrast here. I want to focus on pKa and pKb in red there. And the formula is, right, if you see the little lowercase p, that means you just took the negative log of something. In this case, I'm going to take the negative log of the Ka value. And that's just going to be, I'm going to do hydrofluoric acid as an example. So I insert the number, I plug it in on my calculator, and I get another number. Great, 3.17. Actually, okay, so I have this value. And again, right, when you take the log of something like this, the value of the exponent is a little bit bigger than the actual logged value. By the way, on the calculator, most of y'all have, I'm sure, like a 4-line display, at least, graphing calculator. Usually on those, make sure to hit the negative log button, well, the negative button and then the log button, and then enter that using the EE button for scientific notation. Otherwise, you're going to be off by, it may just give you an error, that's possible, or you'll be off by a factor of 10 or so. So one thing I would encourage you to do, if you're sitting there like, what is he talking about? Plug that into your calculator. Not necessarily right now. After class you can do it because we'll have time, I think. But just make sure that you see how to the sequence that you need for plug and chug on the calculator. Okay. Hopefully it's clear. You can't use your cell phone on the test, right? So you need to use a calculator on the test, please. Let's do the same thing for the pKb. And in some ways, we're just playing games with math right now. But I want to show you that there is a pattern that develops for this kind of thing. Okay, so the pKb for fluoride is 10.82. If I do this for just a couple more, I'm not going to plug and chug the formula. I'm just going to write the answer here. Yeah. Now when I did, like, what's it doing there? Those answers there, I actually plugged it into that formula. Okay, so I didn't use the 14 minus pKa. I actually used that full expression down there. Because, like, if you go in here and let's say over here, if I add up those two values, it becomes a redundant mess. Oop, and it's not. So it doesn't matter what any, take any weak acid and its conjugate base, add the pKa and pKb together, and it'll be 14, basically. So that's where that very useful formula comes from that we'll use quite a bit. Okay? There are other ways to do it. We'll talk about that later. I don't want to talk about it right now. The other way to do it is actually to solve for that equation with the Kb and Ka. The reason why I'm focusing on the pKa and pKb is because the textbook does not do it enough. Once you get out of this class, you never see Ka and Kb. You always say, actually, you always see pKa for everything. You don't really see many tables of a pKb value because you have this equation that allows you to calculate pKb from the pKa of the acid. Anyway, pKa, pKb, what we're going to talk about. Just a couple little patterns. So, small pKa, that means it's more acidic. Large pKa or B is less acidic. And you can do the same spiel. Small pKb, more basic. And large pKb is less basic. And again, that is consistent with the Ka values as well, and the Kb values. Okay. If we go back to the lab for a moment. Actually, let's just take a peek in here. Yeah, I'm gonna focus in on the pH calculation here. There's that approximation, just like I did before, right? There's no X in that final expression. Right? Solve for X, just like before. All right? X is where the hydronium concentration is. A little bit of algebra as you go down there. And just like I said before, right, there's a hydronium concentration, and then you plug and chug into the pH formula. Okay? And again, basically, you do that each time here.
You can just, for that one, drop that sodium out of there as a secondary ion, and your hydrogen there.
Yep. So when we're looking at this particular example here, right, we need to be able to recognize the fact that, okay, when this thing disassociates in solution, we get sodium cations floating around, and we also get this monoprotic charged acid. That's a 7. So this is monoprotic acid. Oops. And then that's what we would insert here into our And you can abbreviate the molecular formula if you want to. Oh, citrate, yeah. Plus H2O, equilibrium. Right, that thing's going to act as an acid. That's the way this is set up. And C6H5O7 minus 2 plus hydronium. And then that sets up your, well, why not? You don't need the block under the water because it's not involved in the reaction. Or, sorry, it's a pure liquid that's omitted from the expression. Positive X, minus X.
Will it have a -3 charge?
Yes, thank you. Now we have our equilibrium expression in the form of X. Use your approximation. Use that Ka value. And then you can solve for X. And then calculate the pH. So it'd be very similar to that. Very similar to the problem I just did. In some ways, very similar to the problem I'm about to do. Dealing with the base. Now, I do want to point out something here. And I don't have. So, this phenylsulfonic acid, I just needed to find one that fit my need here. It has a pKa of 2-ish. If we go back to the slides just for a second. Right? I said as we get to smaller and smaller pKa's, we're actually getting to a stronger and stronger weak acid. So that 2.1 value means that is going to react in water to a pretty high extent. The ionization percent is going to be well above 5%. In reality, we should use a quadratic formula on that one. But I am not getting bogged down in the quadratic formula any more than I already have today. So just know, go ahead and do this one as normal. I put a little star. I put a little check mark on this one. Or maybe in my notes. I put a little star. Anyway, technically you should use the quadratic formula, but I'm not going to mess with it today. Now, if you're using the graphical method, it will work. It'll just give you the correct pH value. And maybe once we come back around to after the test, I might remind myself how to do that and show you. Yeah.
This might be a silly question, but how can you tell the charge of the...
So for this one, let's go back actually. So like when we have that metal in front, the metal tells us we have an ionic substance. Okay, so that's how we knew. Not just that hydrogen citrate had a charge, but actually it has a -2 charge based on the formula there. Right? You can like use that little flip-flop rule like we did back in chapter 4. Whereas here, since there's no metal in front, that means that we're dealing with a molecular compound. So like this one, and let's for my sanity, instead of rewriting that entire formula, PHS or something. And then once it loses that one proton, then that conjugate base has a single negative charge. So the charge the conjugate base takes on ultimately is based on the number of protons that are lost. All these examples will just be one. Let's talk about the bases now. I'm going to do an example of a base, and that'll be the last thing I do today, I think. So let's just look at sodium phosphate. You got to think about, okay, there's like a two-step process here. One, it's going to dissolve in water. Once it dissolves in water, what's going to be the hydrolysis reaction, if any? Now, there will be ones in this. So let's say dissolve in water. You get 3 sodium cations plus the phosphate. Sodium was not on our list yesterday in terms of acids. Okay, sodium does not affect the pH, but phosphate is going to affect the pH here. Oh well, I got my slides here. Let's just take a quick peek. Right there. Look at that. These things are back now. Crazy computer. Anyway. I'm not giving it much of a chance. I mean, I'm like throwing different apps at it, trying to get the dial it in, and I'm just happy to see hydrogen's back. Anyway, so phosphate, it's fitting in with this category here. It's an anion, okay? And it is not the conjugate base of a strong acid. Therefore, it's going to be basic. Remember that. Conjugate bases of strong acids are not basic. Everything else will be basic.
Oh, because it didn't come off of phosphoric acid, it was a salt down to sodium.
So, yes and no. Yes, in the sense of like it's not coming off phosphoric acid, but later, not today, I don't think I'm going to do it today, but there is a correlation between like I say, what's its mama? What's phosphate's mama? It ultimately came from phosphoric acid. If you add 3 hydrogens back to it, you produce that phosphoric acid. So there is a link, there's a connection between the two, and we'll deal with that later. But still, right? Any way you look at it, phosphate or all the variations of phosphate, meaning dihydrogen phosphate, hydrogen phosphate, none of them are the strong acids, so all of their conjugate bases will be basic. Yeah, where's my strong acid? Those are my strong acids. Right? It's a very, very short list of anions that don't affect the pH. Chloride, bromide, a nitrate, hydrogen. Hydrogen sulfate is a little tricky. It's not basic, I know that. And then the other two are chlorate and perchlorate. Phosphate is not on that list. Phosphate is going to act as a base. And so with that in mind, same deal. With practice, things become very repetitive, and this is certainly the case. Now here, please watch out. If we're dealing with a base, that means that OH is going to be produced in the solution. And that does create an additional step at the end to calculate, right? Because we still want to calculate the pH. So like in these examples, these 3 examples, once you get X, you're going to jump through the same hoops in terms of calculating X. You'll see that in just a second. But X here is going to be equal to, not hydronium, but it's going to be equal to hydroxide ion concentration. So what I'd recommend doing is calculating the POH, and then the pH is equal to 14 minus the POH. Right, there's that formula that I briefly mentioned. Oops. Sorry. pH plus pOH equals 14. pKa plus pKb equals 14. There is and I'll talk about the background information about that tomorrow in class. Right now, it is an equation that we're going to use. All of these equations will be given to you on the test, so you don't even have to write it down in your cheat sheet. Okay? Go ahead.
Are we also doing the ones where it gives you like the pKa instead?
If we have time, I think I'm just going to save that for class tomorrow.
Okay, so
I've kind of gotten enough. I think I've given you enough to sort of start making your way through some of this.
Okay.
I still got one more example to do.
Okay, so we're not, sorry, so we're not doing all of these, just the ones where it's the Ka or the Kb given.
So let me answer it this way. So, like on all of these, you'll be filling out IC table, calculating the pH, and filling out this table. The only thing that we're definitely going to skip is that last page, where it's polyprotic acids, and I'm not even going to talk about it because it's not relevant. But like calculation of like going from a pKb to a Ka or something like that, I want to save the details of that, like for tomorrow.
I apologize. Just for example, the ammonium nitrate one, the first example. So in that case, would we skip that one, or would we?
Oh, so I guess let's skip it for right now.
Okay.
I see you're talking about how to calculate pKa to Ka. I will definitely talk about it tomorrow.
Okay.
A lot of them are like that.
Yes. Yeah, so basically for all of them, only one data point is given, and you have to calculate all the other data points. The details of that, I don't think I'm going to do today, just because that's a long lecture. And plus, I mean, the other lab section needs to hear it too.
I'm confused, I'm sorry.
Go ahead.
So if we're not doing this first one because it has pKa, are we not doing the third one as well for osmosis?
So, I made some incorrect statements earlier. So I thought I would be getting to the point to where we could calculate like Ka from pKa and the Kb from the pKb, stuff like that, so that it would allow you to do the full ICU table today. But I've changed my mind. I'm not going to do that. So tomorrow I will go into the details about how to fill out. I mean, the acid conjugate base, you should be able to do that part from the hydrolysis equation. But the rest of these calculations, like starting with pKa, how do you calculate all the others? I'll do that tomorrow in class.
Okay.
Thank you for those questions. Yep, that clarified my vague comment from earlier. It was on my to-do list, but I still got one more problem to do with a weak base, and I'm not going to burn through 3 hours of lecture. That's just torture. Okay. Let's do a problem that relates to these. Hang on. Did I do? Yeah. Let's. Well, I will say this. Some of these examples, like this one, you could do without further instruction. I mean, once you see this IC table problem that I've cooked up here, the Kb is given in this one, so you could actually do that calculation if you wanted to. But let me just go to my blank pages here, and I just made up a problem here. I want to calculate the pH of a 0.10 molar, something called sodium benzoate. And it, actually, let me just use the formula. Yeah, and that's really all I got. And the other bit of information, oh yeah. So I guess I am doing a little bit of this today within this problem. Huh. Doesn't like that. As I mentioned earlier, once you get out of this class, you never see, well, no, not never, but any kind of reference to acidity or basicity of a sample, it's always in reference to a pKa, okay? And this is kind of how the information will be given to you. You got the concentration of some salt. We want to calculate the pH of that thing, okay? That's going to require an ICE table. This is going to produce a basic solution. Kb is not given. Instead, what you're given is the pKa of the conjugate acid. That's what you're given. So like the base in here, that goes into solution, you form that ion. That's C7H5O2 with a negative charge on it. That anion is not an anion associated with the conjugate base of a strong acid. Right? It's not on that list, therefore it will cause the solution to be basic. Or more general, I can say it'll cause the solution's pH to change from 7. If you assume the water that you start with has a neutral pH, which is a good approximation, then you know that this thing is going to affect that. And the way it's going to do it is this guy here. Write a hydrolysis reaction. These anions are basic, so they're going to produce a basic solution. Hydroxide is going to produce. Hydronium is not produced in this. Up. Scratch that out. Here we go. And if I just pause for a second and take a peek at this problem, notice I have a connection here. Right. Embedded within that hydrolysis reaction is its conjugate acid, and it's the conjugate acid pKa that we need to actually calculate this thing. That link between the pKa and the pKb right, that spiel that I just went through there, the relationship of that. Oh, where is that thing? There it is. That relationship of pKa, pKb equals 14. That is associated with an acid conjugate base or base conjugate acid pair. Doesn't matter how you're describing that. They're linked. They're linked together. Yep, not that way. They're linked together. So I guess I am going to show you how to do some of these calculations. Okay, so just know we can pull the Kb out of that. We'll do that in a minute. First off, let's just set up our ICE table. We don't have to worry about water because it's a pure liquid. Good. This becomes extremely redundant, you know. Like when I made this lab, I mean it's the same table over and over again. I see. Initial concentration 0, 0. Which side is going to gain? Good. The product side. How much is it going to gain? It's going to gain X, some value. How much is the reactant side is going to lose? Well, same value, X, because the molar coefficients are 1 in these hydrolysis reactions. I set up my little expression. Now, since I'm talking about hydroxide in there, it's a kind of subtle here, but it's Kb technically. But it's the same form. It is the concentration of that conjugate acid, 7H5O2, times the concentration of hydroxide over the concentration of the base. Like that. It's always that equilibrium line. It's going to be inserted into that expression. Practically always looks like X over that. After test 2, we will worry about it. Up through test 2, you can always use your approximation. If you try to solve for X this way, along with the Kb that we'll do in just a second, you get the quadratic formula and you're like, ABC, I hate these things. God, there's ways to handle it if you want, but anyway. X squared over concentration equals now a Kb value. Let's talk about that Kb value. How do we pull that? How do we go from this to now some Kb value that we can then insert into the formula? I'm glad you asked. Let's do that. I'll do this down here. So Kb question mark. Ooh, that's a terrible question mark. Okay. So we know the pKa, that is a number, 4.20. We know this formula is true, 14. So, you know, I see Kb embedded within that, so I'm going to solve for the pKb. That's pretty good math. Huh. You see a little artifact on this? Is that showing up on the screen? Yeah, look at that. That's from my iPad. That's from the app. Do you know there are apps you can, I probably do, this old guy like, oh, did you know? An app that mimics a hair on the monitor? That is so funny to me. That's perfect. So like the dude on, is YouTube, right, sure. He's like, oh, do this to your buddy. I'm like, that's pretty funny. What's that hair doing? Okay. That math is not too bad. I get well, actually, let me just rewrite the thing. pKb of now 9.80. Okay. Okay, this is the new part. To go from pKb to Kb, which is what we need, right? It's the Kb. It's always dealing with that mass, law of mass action expression. That formula, I'll just give you the sort of the quick spiel. Take 10 and raise it to the minus Kb. Or I'm sorry. Yeah, we have the Kb there. 10 raised to the minus 9.80. And that equals 1.58 times 10 to the minus 10. Right, I said the exponent of a number, well, actually they're pretty close. minus 9.8 is close to minus 10. But you need this. Actually, you could use that form, but it's really awkward to work with. Once something in scientific notation and you're using the proper form, that EE button that you find in your calculator, then your calculator knows what you're trying to get at. The other way to do it is do the second function log. So like 10 raised to the negative 9.8, that'll do it. Or second function log minus 9.8. If you look at your log button on your calculator, the second function is probably something like that. They are complementary mathematical expressions, or I think that's the right term. I'm not a mathematician, so I'm always grasping for terms. Oh, I have my number. 1.58 times 10 to the minus 10. I have it. I'm so close. So close. So now the form of this expression, just like all the others. Solve for x, and this x is going to be right there, 3.97 times 10 to the minus 6. And that is, remember, right, it's that x value. Oops, not that. Up. Let me circle it in green. Anyway. So I still don't have the pH, but ever so close. We know pH plus POH equals 14. So my recommendation is to convert this to the POH. And I think I did that. There it is, 5.4. 5.40. Oh, actually, I need another decimal. Dang it. Well, I don't have another decimal, so I should have another decimal there. Yeah, that's fine. And so now to get the pH is 14 minus the POH. Not that. 14 minus 5.40. And now the pH comes in at 8.60, which is a basic solution, which is what we should anticipate because we're producing hydroxide. Whew. A weak base, you're going to jump through a lot more hoops, many more hoops than with a weak acid. And I'll just say that is the most common error that I see. You forget to jump through the hoops. You forget that, oh yeah, hydroxide throws a big monkey wrench into the whole process. Once hydroxide is present, you got to think, okay, I got to find the KB. That's not going to be given to me typically. Now, there's tables in the book that show some KB values, but if you look at on like the equation sheet, and oh well, I do have this. Oh, I got this on my PDF here. If you look on the Drylab, that's the reality outside of Gen Chem 2. This is the last page of the lab that we're doing. But you're given these different pKa values for the different acids there. We didn't talk about this, but for like the triprotic acid, you get multiple pKa values. But you take this information and you convert it to the KB to then do these calculations. Yes?
I feel like I missed something really simple, but did you end up calculating the Ka for that last
I did not have to calculate the Ka for that one. Yeah, we can do that. Yeah, so like right here, to calculate the Kb, I just took 10. Yeah, good. Yeah, so Ka is 10 to the minus pKa. So I did I did talk about enough to fill out these tables here. You're just doing like negative logs versus 10 raised to a value.
So pKa plus pKb is 14, but not Ka plus Kb. Okay.
Correct. And Ka plus Kb is equal to 10 to the minus 14.
Okay.
Like, and then if you like took a log, if you took a negative log all the way through there, pKa plus pKb, that's where that 14 is coming from. All of these equations are in the notes. They're in the, if you look on Moodle, under the test resources, the equations for the test, all equations for the test, I think is how I phrased it. You'll see all of these equations. Where are they? Oh, there they are. They're kind of sitting right there. There's that 10 to the minus 14 one right there.
That says Ka times Kb equals 1 times. Is that's
Oh, that's correct. I goofed.
Okay.
Thank you. Where did I put that? Oh, wow, yeah. That's really bad. Thanks.
So are all of these ice tables gonna look virtually the same?
Yep. Yeah, that's why I like. So yeah, since the ice table looks the same, basically the quadratic formula looks the same. So that's how, if you have so like dealing with a quadratic formula or really any calculation, if you can get your calculator to do this, it's actually easier just to not use the approximation. But you can plug in. Oh, pooey. It's solving for the quadratic formula without having to graph. There's a lot of calculators can do that. Some calculators some calculators you got to plug in A, B, and C from like the quadratic formula to get the roots. They call them the roots, the answers. But yeah, the student that showed me all this, well, specifically the graphing, he just had the two formulas. Well, he had one was a constant, Ka or Kb. I mean, that's one of the plots. And the other formula, yeah, it just looked like that. The x squared. He just had this formula plugged into his calculator. And like I said, he would just go in and just change the concentration for whatever problem. And then on the other plot, he would just plug in the Ka. So he wasn't even doing an IC table, actually.
So you just plug in x squared over 1 minus x equals
Yeah,
20.
and it just solve it.
Yeah. Give you a graph and intersection point. Is what
Yeah.
Yeah.
So if you can get proficient with that, it's very useful. Sometime after, this is not on test 2, so you don't have to worry about the quadratic formula. Okay, so the approximation will work on test 2. And then after test 2, we'll come back to it. And I'll try to get out my calculator and remind myself how to do that.
Are you making like a review sheet like you did last time?
Yep, and I'll do a little video and all that.
Thank
Yep,
you.
yep. Yeah, I got to cobble together that review sheet. I'm doing a little bit differently than I did 2 years ago whenever I taught this class. Whew. So that's all I got. So yeah, hour and a half, that's about as much as really anyone wants to hear me talk, including myself. So with that, I'm done. if y'all want to, really, it's up to